in R, in R, suppose suppose that suppose suppose that suppose that M is suppose that M is M is a maximal ideal. M is maximal. M is a maximal ideal in R. Ideal in R. So R by M is field. So R by M is commutative. R by M is uh, R by M is a field. A field. So this is the field. R by M is commutative. Commutative. So this property A plus M, comma B plus M belongs to R by M. So A plus M into B plus M is equal to. So according to definition, AB plus M. So again, AB is equal to BA plus M. Since R is commutative, AB is equal to BA. Okay. BA plus M, B plus M into A plus M. So A plus M. So therefore, R by M is commutative. R by M is commutative. R by M is commutative. So second one, R by M as a unity element. So unit element, that's right. So unit element. R has a unity element. So 1, then 1 plus M belongs to R by M. So R by M. For A plus M belongs to R by M. So A plus M belongs to R by M. So this is A plus M into 1 plus M is equal to, so A into 1 plus M, A plus M. Okay. So this is 1 into M, A into 1. So 1 into A, sorry, A into 1. So A into 1. So plus M. Next to 1 plus M into A plus M. So is equal to property 1 into A is a plus M is equal to A plus M. So unity, therefore, so A plus M into 1 plus M is equal to, what is show me? A plus M is equal to 1 plus A into 1 plus M into 1 plus A. So therefore, 1 plus M as a unit element is unity in R by M. In R by M. So in R by M. So in R by M, next, let third condition. Let. So I am taken A bar is equal to A plus M. So be a non-zero element. A non-zero element. Non-zero element. So in R by M is equal to R bar. So in R bar, in R bar. So then A bar R bar is a non-zero element. So then A bar is a non-zero ideal. A bar R bar is a non-zero ideal. Non-zero ideal. So non-zero ideal in R bar. So that's right. So M is a maximal. M is maximal. M is a maximal. Therefore, M is maximal. So this is a maximal. So this implies R by M is equal to R bar as no non-trivial ideas. That is, so R bar, that is only M and capital M and R bar as a non-trivial ideals. So A bar into R bar is equal to R bar. So R bar is a simple ring. R bar is a simple ring. Simple ring. So therefore, 1 bar is equal to 1 plus M belongs to R bar is equal to R by M. So 1 bar belongs to A R bar. So therefore, then 1 bar is equal to A bar into small r bar. A bar is belongs to small r bar belongs to capital R. So R bar is a commutative. 1 bar into A bar into R bar is equal to R bar into A bar. Since R bar is commutative, so commutative. Therefore, R bar is a A unit element. A unit R bar is a multiplicative inverse. Multiplicative multiplicative inverse of multiplicative inverse of A bar. So therefore, R bar is equal to R bar is a R by M is a commutative ring or ring with unity. Is a every non-zero element multiplicative star. R bar M is a field. This is a field. So first of all, prove that this is a commutative ring. R by M is a commutative ring. R by M is a unity element. R by M is a every non-zero element multiplicative inverse. We have 1/3. Therefore, R bar is equal to field. Next is conversely. Conversely, conversely, suppose that R bar is equal to R by M. R by M is a field. Is a field. Is a field. R bar has no proper ideals. No proper ideals. No proper ideals. Let K be any ideal in R. K be any ideal in R such that so M subset R equal to K subset R equal to R. First one, R by M field. R by is no proper ideal. K be any ideal. M subset of K subset of R. Now, R since M subset of K, so K by M is a non-zero element, non-zero ideal, non-zero ideal. So non-zero ideal in R by M. So such that K by M is not equal to multiply to M. So this is M not equal to K, M subset R equal to K. K by M must be equal to R by M. So this is K by M is equal to R by M. So this implies K is equal to R. M is a maximal ideal. M is maximal ideal. So M is a maximal ideal. This is the way. Now, so the SCQ question 3.34. So for any positive integer, n belongs to positive integer, to the following are equivalent. First one, m is prime number. n is a prime number. N is a prime number. Second one, the principal ideal nz. The principal ideal nz. So is a maximal ideal of z. Is a maximal ideal of n is a prime number. The principal ideal nz is a maximal ideal of z. The ring Zn of integer modulo n is a field. Is a field here. So if is a prime number. So this is a first of all, we note that necessary n greater than 1 of the properties is true. So we can assume that n greater than 1 implies to 2. So 1 implies to 2. Suppose A belongs to Z minus nz. So the n does not divides A, and since n is a prime, hence GCD of A comma n GCD1. So what is the formula? Or n comma A, or this is a GCD n comma A. So what is the there exists a integers x comma y. So x comma y integers x such that nx plus ay is equal to 1. So x comma y integers. So this is nxy. Therefore, it's a nz is a maximal ideal. Nz is a maximal ideal. Okay. Now, second is so 1 implies to 2. Next to 2 implies to 1. So A belongs to uh, z minus nz. So this implies NA. So the GCD of n comma A is equal to 1. So what is the definition? Nx plus Ay is equal to 1. For some xy belongs to z. So 1 is a belongs to nx plus Ay. So nx plus Ay is equal to z. This is the second. Now second implies to third. So let 0 is less than A is less than n. Then I'm taken A does not belongs to nz. Since nz is a maximal ideal. Maximal ideal. Nz is a maximal ideal. Nx plus Ay is equal to z. So this is xn plus ya is equal to 1. X comma y belongs to z. So y is equal to qn plus r. This is a dividend. The dividend is equal to divisor into quotient plus remainder. 0 less than or equal to r less than n r not equal to r. Otherwise, n divides of y. Other divides n and hence n divides of 1. It's the okay. N divides of 1. N divides of 1. N divides of y. N divides of r, which is a contradiction. So 1 minus of RA is equal to xn plus qn. And hence RA is congruent to 1 modulo n. So on. This is A is a invertible. A is invertible. Invertible in Zn. So Zn is a field. Invertible and Zn is a field. So Zn is a field. So 2 implies to third. Next 3 implies to 1. So 3 implies to 2. Now if 1 is less than A is less than n, there exists B belongs to Z such that 1 less than or equal B less than n. So therefore AB congruent to M modulo n. So since Zn is a field, Zn is a field. So we can field. So n divides 1 minus AB. So n divides of 1 minus C. A divides of n. A divides of 1. And which is a contradiction. Therefore 1 is less than A. Wrong. Therefore n is a prime. So 1 is less than A. So A divides n is a prime. This is wrong. 100% we should be n is a prime. N is a prime. So this is R implies to, it's a clear. Now again, next is the theorem is Let X be a non-empty subset of F and R be a ring of mapping of X into F, then R is under usual pointwise operations. This is M is a maximal ideal. X is a finite, every maximal ideal of R is a form. M, since X is a infinite, then it is a different offer. It's not important, this theorem, 3.3.5. So next is definition is 3.3.6 is ఫోన్ ఇచ్చిందా ఫోన్ ఇచ్చిందిగా ఇంకేమన్నా టిఫిన్ బాక్స్ ఓకే అడ్రస్ చేసుకో అడ్రస్ చేసుకో let R be a ring. The intersection of all maximum elements R is called as a Jacobian radical of R. Jacobian radical of R అంటే R is a ring. R is a ring. So R is a ring. The intersection of all maximal ideal. The intersection of all maximal ideals. All maximal ideals. So maximal ideals. R is called. So the Jacobian radical. So the Jacobian radical of R, and is denoted by J of R. So if J of R is equal to a singleton 0 or multiple, is called as a semi-simple ring. So the RBA ring, the Jacobian radical of R is given by J of R is a unity element of also. Okay. In 3.3 important 3.37 theorem. 3.37 theorem important. Let R be a ring. The Jacobian radical of R is given. This is the Jacobian radical of R denoted by A belongs to R such that 1 minus AX is a unit. For all X belongs to R. This is important. 1 minus AX is a unit. So this is a proof, Jacobian. So it is a proof is now it's clear from. It is enough to show that A belongs to R. Let for any A belongs to R, A does not belongs to Jacobian radical of R. This is if and only if 1 minus AX it is not equal. 1 minus X is not a unit. Is not a unit according to definition Jacobian. Jacobian కావాలంటే compulsory 1 minus X unit. 1 minus X is not a unit. For some X belongs to R. For some X belongs to R. For some X belongs to R. Okay. For some X belongs to R. For some X belongs to R. Let A belongs to R. Suppose A does not belongs to Jacobian R. Then there exists a maximal ideal. Then there exists a maximal ideal. So a maximal ideal, maximal ideal, M of R. So M of R such that A does not belongs to M. A does not. By maximality of M, MA plus the maximality of M. The maximality of M. So by the maximality of M, so maximality of M. So this is M plus RA is equal to R. And what happened is this is M subset R equal to M plus RA subset R equal to R. M is a maximal ideal. M is equal to R. So this is not possibility. M plus RA is equal to R. In particular, so R is 1 belongs to R is a ring with unity. So 1 plus M plus RA. Then 1 is equal to small m plus XA. So where is the X is belongs to R? So where is for some small m plus XA. Small m belongs to M and X belongs to R. And then 1 minus AX. 1 minus AX. So 1 minus AX is equal to small m. Small m belongs to capital M. So M is a proper ideal. M 1 minus X, 1 minus AX belongs to M. Kani manakem telsu this is called is a not unit. Since M is a proper ideal, M is a proper ideal. So proper ideal. Therefore 1 minus AX is not unit. Is not a unit. So therefore 1 belongs to, otherwise M is equal to R. So we have to prove is not a unit. 1 minus X is a not a unit in proof. Conversely, so మనం ఏం తీసుకున్నాం, హెమిస్ Jacobian ring తీసుకొని we have to prove 1 minus X is a not, otherwise in conversely, otherwise 1 belongs to M is equal to R. So it is we prove it. Next is conversely part. What is a conversely? This is a conversely. So it is conversely. What is a conversely? Is suppose for some X belongs to R, so 1 minus AX is not a unit. The principal ideal generated by the principal ideal. So the principal ideal generated by 1 minus AX. So the proper ideal, this is contained in maximal ideal. 1 minus AX is belongs to capital M. So which implies is 1 minus AX plus AX is belongs to capital M. This is MM. 1 belongs to M. This is M is equal to R, which is a contradiction, or therefore implies that A does not belongs to M. So M is a, this is what. Jacobian 3.38 SAQ. Determine Jacobian radical of the following: the ring of integer, the ring of real valued function set X, the ring Z2 is integer mod N. Now, so first of all is in 3.3.38. So it's a equal from this is called is first of all. A belongs to Jacobian ring of R. So therefore then 1 minus AX. So and 1 plus 1 minus A, 1 minus A comma 1 plus A are both units. Are both units in R. So therefore 1 minus A is equal to plus R minus 1. 1 plus A is equal to plus R minus 1. So therefore, what is the situation? 1 minus A is equal to plus 1. So what is the called is 1 minus 1 is equal to A equal to 0. One case. 1 minus A is equal to minus 1. We have to apply 1 plus 1 is equal to A is equal to 2. This is the other case. A is equal to. Next is 1 plus of A is equal to plus 1. So what happened? A is equal to 1 minus 1. A equal to 0. So 1 plus of A is equal to minus 1. A is equal to, what happened is minus 1, A is equal to minus 2. And these two cases, we can should be A is equal to. And this is the two cases is possibility. This is not possible. Therefore, A is equal to 0. A is equal to 0. The Jacobian of R is equal to singleton 0. So first part. Now in second, XBA, it is the second part is let a capital X be a set, in R, the ring of functions of X into R are real numbers. By using MX, a functions of F belongs to R, capital X, such that F of X is equal to 0 is a maximal ideal of R. Since the intersection of all small x belongs to capital X, capital maximal of ideal X, so it is a singleton 0. Then Jacobian of R is equal to singleton 0. Now the ideal is generated by 2 and 3rd, the only maximal ideal. So Z12, next to Z12 is generated by, is 2 generated and 3 generated in prime number general. both are maximal ideal of, and it is a Z2 and Z3 is a generator. The both are maximal ideal of a Jacobian radical of generated by, so 6 also, 2 and 3. This is a Z2 is prime number generated. It is called as a maximal ideal. So again, now this is a way local rings. Exactly one maximal ideal unte, that ring is called as a local ring. The ring R over of J R of R is a semi-simple ring. So next is in 3.310 theorem is theorem. For any ring R following are equal to each other. First one is R is a local ring. Second point is R over of J over of R is a field. J over of R is okay. Local ring is R as a unique maximal ideal unte, that ring is called as local. A comma B, A plus B unit, either A or B are unit. The set of all non-units are forms a ideal of R. For any maximal ideal M of R 1 plus X unit all follows. First one, 1 implies to 2. Suppose R is a ring. Suppose 1 implies to 2. Suppose R is a local ring. Local ring. So local ring. R is a local ring. So R has local ring definition. R has only a unique maximal ideal. Unique maximal ideal. So maximal ideal, say capital M, that is J over of R is equal to M. So hence R over of J over of R is a field. So next, 2 implies to 3. What is the 2 implies to? Suppose R over of J over of R is a field taken. We have to prove that. Let A comma B belongs to R. So that A plus B is a unit. A comma B unit. A plus B unit. Since J over of R is not equal to R, either A or B must be, either A or must be, so must not be in J over of R, otherwise is, so it's a way. Now suppose A does not belongs to J over of R, then A plus J over of R is a non-zero element, non-zero element in R over of J over of R. Okay. Which is a field? This is a field. Which is a field. So the field, therefore, the field element. So therefore, the field is X belongs to R. So X belongs to R such that A plus J over of R into X plus J over of R. So two cosets element 1 plus J over of R. That is A plus X. So AX plus J over of R. A cosets multiplication is equal to 1 plus J over of R. Ideal definition is 1 minus AX is belongs to J over of R. So according to definition. So again, 1 minus AX is a unit in R. Unit in R. So 1 minus 1 plus AX. So 1 cancel is a unit in R. AX is a unit. So AX is a unit, I think. So AX and unit, then AX and A is also. AX is unit. AX and A is also a unit element. So first of all, this is the proof is. Suppose R is a local ring. R has a unique maximal ideal. Say M. J over of R is equal to M. So R or J over of is a field. Okay. Now, and already M is a maximal ideal కాబట్టి M is maximal, then R by M is a field. J of R is equal to M కాబట్టి R it is R over of J over of R అనేది should be filled. Suppose second implies to third. Suppose R over of J over of R is filled. A comma B belongs to R. A comma B belongs to R unit element. A plus B is also unit. Since J over of R not equal to R, J over of R not equal to R, either A plus J over of R is a non-zero element of R over J, which is a field. Therefore, field యొక్క definition X belongs to R, such as A plus J over of R, A plus J over of R, X plus J over of R is equal to 1 plus J over of 1 minus AX belongs to J over of R. According to coset subtraction, 1 minus half 1 minus AX belongs to R. AX is a unit. AX is a unit. A is also unit. So next, third implies to fourth. Now, this is third implies to 4. So third implies to 4 is let, this is the ideal. Let I is equal to ideal is A plus A belongs to R. A is not a unit. Not a unit. Not a unit. So clearly, if A belongs to I, A belongs to R, A is not A. A belongs to R, then AX belongs to I. For all X belongs to R. So if we assume 3, so 3 assume, it follows the sum of any non-units is also non-unit. Sum of two non-units element is also non-unit. Therefore, I is ideal. Sum of non-unit elements is also non-unit. So this is a non-unit element. Element is also I is an ideal. I is an ideal. Third card, ideal of R. Okay. Next, 4 implies to 5. 4 implies to 5 is let I be the set of all. Let I be the set of all. Set of all. I be the set of all. I be the set of all. I be the set of all non-units element. Non-units. Be an ideal. Be an ideal of. So be an ideal of R and M. Maximal ideal. So maximal ideal. Then M subset R equal to I subset R equal to R. This is equal. I'm showing this is not possible. This is not. M is equal to I. So M is equal to I. So if X belongs to M, so then 1 plus X belongs is not unit. Is not a unit in M. Not in M. So therefore 1 plus X is a unit. 1 plus X is a unit. So next is 5 and 5 implies 4 implies to 5. 5 implies to 1. So M and M dash be maximal ideal. M and M dash be maximal ideals. Be maximal ideals. Maximal ideals of. So maximal ideals of R. And 1 plus X is a unit. 1 plus X is a unit. So unit for all X belongs to M. So if A does not belongs to M, then there exists B belongs to R such that AB minus 1 belongs to M. So this is 1 belongs to M. AB minus 1 belongs to M. Addition, a closure. 1 plus AB minus 1 belongs to M. AB minus 1 belongs to M. So E is a unit. So this is 1. AB belongs to M. And A is a unit implies AB belongs to M. So A is, and hence A is a unit. A is unit. So A is unit implies that A does not belongs to M dash. So therefore M dash is subset or equal to M. But manakan also M is subset or equal to M dash. Those two equal, M dash is equal to M. So M dash is equal to R is a M and M dash two maximal ideals. We take an M is equal to M dash. I think M is a unique maximal ideal. M is unique maximal ideal. R is a local ring. What is our local ring definition? A ring R is said to be local ring. If it is has a unique maximal, a ring R is said to be local ring. A ring R is said to be local ring. It has a unique maximal ideal. Is called as a is called as uh, is called as a that is called as it is called as a maximal unique local. It's called local ring. A ring R is said to be local ring. It is a unique maximal ideal. So that is called as. So next is it's very very important theorem. This is the 3.311. Let R be a principal ideal. R be a principal ideal. So R be a principal ideal domain. R be a principal ideal domain. Then every non-zero ideal, every non-zero ideal, every non-zero prime ideal, every non-zero prime ideal of R of R is a maximal. Of is a maximal. So of is a maximal. This is the proof. Okay. So it is a clear. Uh, Inca, we tell me this is RBA ring with unity. RBA ring with unity. RBA commutative principal ideal domain. Then a non-zero prime ideal. P is a if and only if maximal ideal. So let RBA this is. So let RBA principal ideal domain. RBA principal let RBA RBA PID principal ideal domain. RBA PID means a ring which all ideals are principal ideal. That ring is called as a principal ideal domain. RBA a R plus comma dot a ring in which all ideals R plus comma dot in which all ideals is principal ideal is called as a principal ideal domain. R is a that is R is a commutative. R is commutative. So R is a commutative principal ideal ring. Principal ideal ring. So principal ideal ring. So principal ideal ring with unity. Principal ideal ring with unity. So let P not equal to R. So be a maximal ideal. Be a maximal ideal in R. Be a maximal ideal in R. So let A comma B are two ideals. Two ideals in R such that AB subset are equal to AB subset are equal to AB subset are equal to P. Now we have to prove that. Now we have to prove that. Now we have to prove that A subset R equal to P or B subset R equal to P. So suppose A not subset R equal to P. So P subset of, this is P subset of A plus P subset R equal to R. So this is equal. And because therefore P is a maximal ideal. Maximal ideal. P is a maximal ideal. P is a maximal ideal. So therefore AP plus A plus P is equal to R. So A plus P R. One belongs to R. This implies one belongs to A plus P. Then one is equal to small a plus small p. Small a plus small p. Small a plus mm, small a plus small a small p. Small a. So that is called is small a belongs to capital A. Small m belongs to capital P. So let x belongs to B. Then x is equal to 1 into x. So x is equal to 1 is a plus m into x. So this is ax plus mx. ax plus mx. So ikkada small a belongs to. So x is equal to, this is the concept. We can do, right? This is small a belongs to capital A. Small x belongs to capital B. Ax belongs to AB. So Ax belongs to AB. One concept. Small m belongs to capital P. X belongs to B. X belongs to B. X belongs to B. Mx is belongs to P. P is ideal. P is an ideal. So these are addition. So already x is equal to ax plus mx. So this is x is belongs to ax is a value AB. Mx value is P. So AB plus P. AB plus P. So AB plus P is a means. This is AB subset R equal to P. AB subset R equal to P అయితే AB plus P is equal to P అంటే AB plus P x belongs to P. If I am taken x belongs to P, this implies x belongs to P can show me. So AX belongs to AB, MX belongs to P, x is equal to AM ax plus mx is belongs to P, ax is AB plus P. AB subset R equal to P, AB plus P is equal to P, x belongs to P. If x belongs to P, x belongs to P. And what happened is B subset R equal to P. B subset R equal to P. Whenever is, we can show me when I am to take it, A not subset R equal to P, A not subset R equal to P, so that B subset R equal to P. Similarly, we can prove that. Similarly, we can prove that B not subset R equal to P, we can show me A subset R equal to P. Koti, we can do. Therefore, AB subset R equal to P, this koni, then prove that. A subset R equal to P or B subset R equal to P. Therefore, hence P is a prime ideal. P is a prime ideal. So next conversely part. What is a conversely? This is a conversely. What is a conversely? So it's a clear. This is what is the property? This is R is a PID, principal ideal, a commutative principal ideal domain. P is not equal to 0 prime ideal. P not equal to M. So prime ideal అయితే so ideal if and only if is maximal. P is maximal ideal. So maximal. ఇక్కడ నేను maximal ideal తీసుకొని prime ideal దించాను. It is a conversely part. Now again, no. This is the conversely part. What is the conversely? This is conversely. So conversely. Suppose that suppose that P not equal to R be a non-zero, be a non-zero, be a non-zero prime ideal, be a non-zero prime ideal in, so prime ideal in R, prime ideal in R. We have to prove that. So we have to prove that. We have to prove P is maximal. P is maximal. P is maximal. If he possible, if he possible, if he possible, so if he possible, suppose that, if he possible, suppose that, if he possible, suppose that P is not maximal, P is not maximal, then there exists an ideal, there exists an ideal in R, ideal M in R, such that P subset of M subset of R. So therefore R is a principal. R is a principal. ఇప్పుడు taken తీసుకొని we have to prove maximal and M is equal to R prove చేస్తే సరే. This is not possible. This is a possible. Is possible. కాబట్టి only we have to prove M is equal to R. M is a maximal. R is a PID, principal ideal domain. What is a PID? In which Hall rings? A ring which all ideals, a ring which all ideals are principal ideal is called a ring principal ideal. A ring which all ideals is called is a principal ideal. What is a principal ideal? R is a principal ideal ring with unity. Every ideal is a principal ideal. That is called as a ring with unity. So we have P is a ideal. P is a prime ideal. Prime ideal and prime ideal is means before is ideal. And P is equal to what is a single element. A single element generated called is principal ideal. Principal ideal, PR. For some, so P is equal to R. We have then for some A comma B, P is equal to R, M is equal to BR. These are two principal ideals. So where B does not belong to M. P is subset of M, A R subset of BR. So A small a is the element of AR, subset of BR. So this is small a is the element of BR. So then B A is equal. So A belongs to AR, subset A belongs to BR. Then A is equal to B into small r. For small r belongs to capital R. This is equation 1. P is equal to AR. P is equal to AR. So BR is equal to A. A belongs to AR. So BR belongs to BR belongs to P. Ante what is a BR belongs to P. So ఇక్కడ BR belongs to BR is equal to A belongs to AR belongs to P. So BR belongs to P. So this is 100% R belongs to P. And since B does not belongs to P, B does not. R belongs to P. So P is equal to AR. So R belongs to AR. So then small r is equal to, A small r. Where is the small r belongs to capital R. So A is equal to BR. So A is equal to B into A R1. So B into A R1. R1 belongs to A R1. So like that. So A is equal to like that. AB of R1. So A cancel. 1 is equal to BR1. So 1 is equal to BR1. So by left cancellation laws, 1 is equal to BR1. So 1 is equal to BR1 by left. BR1 belongs to BR. BR is equal to M. So 1 belongs to M. So 1 belongs to M. M is an ideal. So M is an ideal. 1 belongs to. So already BSc 1 theorem. 1 belongs to U is ideal. U is an ideal. Then U is equal to R. Suppose X belongs to R. So X is equal to X into 1 is a belongs to capital M. M is a since ideal. And X belongs to M. Then R subset R equal to M. And M already subset R equal to. Then M is equal to R. So I am to taken. So M తీసుకున్న P subset of M subset of R తీసుకొని we have to prove M is equal to R. Then P is called as a maximal ideal. So P must be a maximal ideal. A maximal ideal. Maximal ideal. అంటే P prime ideal అయితే maximal ideal అవుతుంది, maximal ideal అయితే prime ideal అవుతుంది. There if and only if. This is a possibilities only from This is a possibility is only P primordial, then P maximal. Then P maximal converse and P primordial also. Whenever is the possibility is only PID, a commutative ring principal ideal domain. A commutative ring principal ideal domain low, this is the possibilities of theorem. So this theorem is, it is 3 point, this is the theorem is 3.311 is the theorem is coming. Extension and contractions. So extension and contractions definitions. Uh, no. So this is the topic is F is mapping from R to S. Be a homomorphism. Be a homomorphism. So of a rings. For any ideal I of R is generated by f of I. This is generated by f of I. In the S is called is the extension of I. S is called is f of I. S is called is generated by f of I. In S is called, X is called is extension. S is called extension of I. I is an ideal of R. I another ideal. F R to B is a homomorph. I is ideal of R. F of I is also generated by f of I in S is called is I with respect to, and therefore S is called extension I. S is called extension I with respect to F is denoted by, so I S is called is extension I power of C, extension I power of E is our extension I power of E small e extension. So with ideal denoted by for any ideal J. ఇప్పుడు ఐడియల్ డొమైన్ ఐడియల్ FR mapping from R to S. I is ideal of R తీసుకుంటే then S is called is extension of ideal of extension of I with respect to F. It is denoted by I power of C. ఇప్పుడు J is ideal of S తీసుకుంటే J is ideal of S inverse mappage. ఈ F inverse of image of J is ideal of R. F inverse of image ఏమవుతుంది? F inverse ఎక్కడికి వస్తుంది? This is inverse mapping from S to R. So we are taken J ideal. F inverse of J అనేది ఏమవుతుంది? This is called this. Is an ideal in R. Is an ideal in R. Is called contraction. Contraction J with respect to F. It is denoted by J power of C. J power of C is means contraction. Inverse mapping is contraction. Original mapping is called is extension. So F is mapping from R to S be a homomorphism. R is a domain ring. S is a codomain ring. I is the ideal of R. Then S is called is extension of I with respect to F. It is denoted by I power of E. Inverse image F inverse of S to R be a homomorphism. J is the ideal to S domain. Then F inverse of J, ideal of R, is called is contraction mapping of J with respect to F. So with respect to F, it is denoted by high power of E, J power of C. So what and so interaction. This is high power of C. This is a high power of C is equal to the summation of I is equal to I is equal to 1. This is SI f of AI, SI f of I, such that n greater than 0. Small si belongs to capital S, AI belongs to S. అంటే ఇక్కడ what is the meaning? Contraction, I power of E, uh, I power of E extension, I power of E extension. So F is mapping from S to R to S. R to S is be a homomorphism. SI FR, where is the small SI belongs to capital S, small AI belongs to I. Okay. Contraction, J power of C, small r belongs to capital R, such that F of R belongs to capital J. Capital J is a, ikkada what is the discussion is F inverse of mapping. F inverse is a mapping from S to R. Ikkada J is a ideal of S. So a small r belongs to R, F of R belongs to J. The image S set B belongs to J. So F R to S is a epimorphism by the fundamental theorem of homomorphism R by kernel F isomorphic to S. So J to uh, J contraction, bijection, the ideal source also. I to extension. So it is also I to extension is the inverse. So high extension of extension extension mapping is equal to I. Extension of I is equal to I. Ideal of R contain. J contraction to extension is equal to J. This is all. ఇక్కడ J high extension of I is equal to I. J extension to contraction is equal to J. This is a way. Prove all the details this way contraction. Now Gaussian integers in integers. The ring of Gaussian integer, V operation, the usual addition complex number, recall here. 1 and -1, high and minus I are the ring of Gaussian integers are inclusion map. So consider inclusion map. F is mapping from Z to Z over of I. This is a mapping. Is denoted by F of X is equal to X. So for all X belongs to Z, you know the prime number P, Pz of multiples of prime ideals. The following section extension P of Z of extension of P of Z into Z over of I Gaussian integer is not prime ideal Z of I, it's a extension. So this is the way extensions are mapping. So extension contraction. So it is an explanation this way. Now. So this is a page number is 53. High extensions to contraction is equal to high extension to power of contraction is equal to IEC and I extension to contraction is equal to A belongs to R such that F of A is equal to summation of I is equal to 1 to N SI F of AI. So SI is belongs to capital S, AI is belongs to capital I. So this is a J contraction to extensions is equal to J power of contraction to extension. So is equal to summation of I belongs to N, SI, FI, F of AI, such that SI belongs to S, AI belongs to R, F of AI belongs to J, N greater than 0. This is the, according to the definitions are contraction junctions. We can see this is the topic is contraction J, it is a theorems. Now, this is a contraction. You can tomorrow discussion. Next to prime spectrum. Next class is tomorrow. Har modulo har I will do discussion. T1 space spectrum kante we can do discussion is tomorrow, elementary concept of modules. I will tell discussion tomorrow, modules of R. Okay, today